Hello, everyone. My name is Jaskaran. I'm a group member in Group 5, and today we will be speaking about our license plate sensor. And I'll pass it off to the rest of my teammates so they can introduce themselves.
Hi, everyone. I'm Ryan Kelly.
Blake Baxter.
And I'm Alex Stoica, and I want to talk to you about our license plate censoring program. So again, a little introduction to what we're going to be doing with the program and why we thought of using it. So first off, there were lots of a variety of reasons, whether it be privacy protection or helping in social media. News programs like to blur out their license plate every single time they're showing videos. And if you're a vehicle owner and you want to take a quick video or picture of your car, you don't have to worry about going into Photoshop, paying the subscription to start Photoshop and then blurring out your box. It's just a nice little hassle-free option. And we're going to be doing that by detecting a license plate and putting a black box over it. And someone like, how Google does their Google Earth, they show their cars and they blur it. We put a black box over it, and I think that kind of sets us over Google because black boxes are more secure than just a blur. And we use this with OpenCV and Python, and we want to show you a couple demos of our program. Oh, so here it is. That's censoring it. That's it. I'm just kidding. So let's start a video of our license plate sensor. This are our group mates, and our first one is just, you're going to see a stationary vehicle. This is one of our personal vehicles. And you can see we have 3 different pictures. The one on the right is the censoring. And now we want to show you a video where we're obstructing the view. There's a little bit of detection errors that we're going to talk about later in the presentation. And here it is with us backing the car. And I actually want to pass this on over to Jaskaran for a live demonstration.
Thanks, Alex. I will start sharing my screen so I can show you how it works in real time. So actually, instead of bringing my webcam and laptop outside to show a view of my car, I actually just unscrewed my license plate and taped it to some cardboard so I can hold it up hands-free and let you guys see it being censored in real time. So here it is, and you can see on the rightmost image that I'm sorry, I didn't flip the screen, so it's a little bit confusing as I move, but you can see that the program is in fact censoring the license plate, and it works at a little bit of an angle, and I can hold it up to the webcam and it will find it and censor the license plate at quite a few different angles, but there are still some problems that we need to work through. And that's it for the demo, so I will go ahead and pass it back to Alex.
All right, let's get back into it. So when we started our presentation, we had a lot of different approaches, each with their pros and cons. And our first one, the one we decided to implement, was detecting rectangles. This was, as you'll hear a lot with these presentations, time constraint is a very big commitment you have to factor in. So detecting rectangles was one of our most admirable solutions to something we want to approach because it's a quick and easy solution. We can troubleshoot it if we finish it. And it's really accurate, like when the license plate is close and squared to the camera, but then there's some issues when there's some lighting changes, there's obstruction. And you saw that with the live demo and even the demo video. And we're going to talk about how we implemented our code and why that came up. Another solution was detecting text, whether it be just looking at the text of license plates, we're analyzing them and then we're censoring everything around them. There was a solution we found online that worked fairly well. That was just for images, however. So taking it into videos, although it would have been pretty simple, it's just they gave us it in pictures and we didn't want to just use some online thing we saw. So we created our own solution with the detecting rectangles. And then as we reached the end of this project deadline, we found out that machine learning would have been a very viable solution had we that extra time. And these were the 3 different approaches we could have taken. And in an ideal world, we would have implemented all 3. And we're going to stick with the first one, and we're going to talk to you about our approach.
Okay, so as Alex mentioned, we did have three possible approaches that we could have chosen, and the one that we ended up going with was to find rectangles in a video frame. So the first step in doing that was to read in the video frame itself and then extract the object edges so we could look for the rectangular contours. Once we find those contours, we would actually with just one simple function, just censor the area inside the contour. And then finally, after we censored each frame in that video, we would just write that censored video to file so that the user can access it easily. So this is, I'm going to go through the code and talk about each individual step, and this is the demo image that I'll be using to talk about it. So can we move on to the next step, please? The first step was extracting the object edges, and the way we did this, can you go to the next slide, please? Was to first convert the frame to grayscale, so we didn't have to look at all three color channels, red, green, and blue. We just have to analyze a grayscale image, and that speeds up processing. The next step was to allow the user to define the filter values. We didn't find a way to automate this process yet, and adding track bars to the GUI was the easiest way that we could think of to allow the user to quickly change these filter values. Next, we removed any noise from the video frame with a bilateral filter. You can see the effect that a bilateral filter has on the two images at the bottom. The one on the left, you can see some texture on the car and on the ground. And after applying the bilateral filter, you can see all the texture has been smoothened out, and that makes it a lot easier to extract the edges, which is the next step. So here's what the image edges look like on the bottom right. And after we pull those image edges out, what we do is we take a dilating kernel and run it over the full image to fill in any boundary gaps that might exist in that edges image. So here is the final dilated edges image that we extracted from the original video frame. So the next step is to go and find the rectangular contours. So this is just as two sub steps. The first step is just to find the contours, and then these two images at the bottom display what the contours that were found look like. On the bottom right, they're displayed in red. And the next thing after we find those red contours would be to determine which of these contours are rectangles, because license plates are rectangles. So we can easily knock out any contours that were found that weren't rectangular and just not have to worry about processing them any further. So in order to determine which contours are rectangles, I use two substeps within this substep itself. And Alex, do you mind going to the next slide, please? So the way to do this is if we find a contour like that bottom left shape, we can just approximate it with a simpler contour like that bottom right shape by running one of OpenCV's built-in functions, and it just approximates the shape with a shape that has slightly less vertices. So this allows for a little bit more robustness. We don't have to look for an exact rectangle in a video frame. So now that we have an extracted contour, an approximate contour, how do we determine if it's a rectangle? And I'll go into that. The first condition we check on the approximated contour is whether it has four sides. If it has more than or less than four sides, we immediately know it's not a license plate. We don't have to worry about processing that contour. So we can eliminate shapes like the top one there. So that four sides condition isn't sufficient to determine what's a license plate. It would allow a shape like the one on the bottom to continue through, and it would, something like that would get censored in the video frame, which is actually something that happened during our testing. It was finding weird four-sided shapes, and we didn't want those weird four-sided shapes to be censored, so we had to implement an additional condition. So one condition that I thought about was we could check side length ratios. Is the width of one side, or is the width on one side of the rectangle divided by the width of the second side on the rectangle? Is that approximately equal to 1? Is the same thing true for the height ratios? If they are both approximately equal to 1, we just assume that the approximate contour is a rectangle. And if it's not equal to, approximately equal to 1, we assume it's not a rectangle and we don't want to censor it. And this condition was sufficient. An additional condition we decided to check was whether we actually wanted to censor every rectangle in the scene. Before implementing any additional conditions, every single rectangle would be censored that was found. And we don't always want that, because sometimes there's rectangles in the grille of a vehicle, or rectangles way in the background that are just too small to read anyway. Even if it's a license plate, we don't need to censor it if it's that far away. So we implemented an additional condition, and that was to check the area of the rectangle itself. And the default condition we have set right now is check if the area of the rectangle is greater than 20 pixels. If it is, we go ahead and censor it. If it's not, we just ignore it altogether. So I've summarized how we determine whether an approximate contour is a rectangle. And if we go to the next slide, you can see from the change in the images, the image on the left shows all the contours that were found. And then if you go to the right, after we've filtered out everything that wasn't a rectangle, you can only see one small blue contour outlined around the license plate. That's the only one that was left in the list of contours. And that's what we assume to be our rectangular contour. So we take that blue contour that was found, the area on the screen in the image, and we fill that area in and simply add that filled in area to the original image to come up with this final censored image. And then if we go next, here's just the last step in the process of us writing the censored video frame to file. The whole video ends up being saved just like this, and it's easy for the user to access. And Ryan will go into the results of our project.
So in order to get our results and test our program, we used images of quite a few different models and makes of vehicles, as well as license plates, front, back of the vehicle, as well as different patterns of the vehicles. So we used personal vehicles as well as images from Google. Here's an image of one of our personal vehicles. This is the user interface after our program is run through OpenCV. We implemented track bars, which include canny filters to get the edges of the image, as well as to dilate the edges in order to complete the rectangle for our program, in order for the contour function to actually detect the rectangle. So in the bottom left, you can see the original image. In the middle, you can see the image that we are trying to change in order for our functions to work correctly. So the user is able to change the canny thresholds to detect the images, as well as dilate these edges in order to get the final product in the bottom right, which is the censored image. So here's a picture of a Lexus. We chose this image because it was taken at an angle, as well as the grill kind of has rectangular patterns. So we wanted to determine that our program would not take into account those rectangle patterns and only detect the license plate, which it was able to do successfully. So here's two of the images that we started with to troubleshoot our program, since they're pretty simple and straightforward. The top one, none of the filters really needed to change. The bottom one, we just had to dilate it more and show the edges. Here's another picture, just a standard picture that worked pretty well. So here's a Mustang, another one we chose because of the grill. The grill looks like a hexagonal, so we wanted to determine that our program would not detect the grill and only the license plate, which it did successfully. And now I'll send it over to Blake.
Okay, limitations. You can see in the bottom right pictures that we actually had a license plate that we could not get to work. We think this is because the color and also the contrast of the around the edge of the license plate pretty much matches the car. So looking for edges on the top of that license plate, we just couldn't get it done. Also, you could see in the video presentation that in any kind of fast motion or severe angle, our edges would not be detected and it would not censor the license plate. Next slide. So talk about future improvements. Earlier, we showed two possible examples using either a text censoring application where we're looking for random letters on a plate and then try to block out a known size in relation to those letters, and also using machine learning. We think there's a lot of risk in just censoring out letters. There's potential to block out pretty much any kind of text within a picture, if it's road signs or anything else in the picture that we don't want to block out or mask. So we think machine learning would have been like the absolute best solution. That would have taken us a whole lot of time and we weren't exactly sure where to start. So using rectangles still was pretty effective. So this is our example of using OpenCV and Python. We learned a lot and felt it was pretty successful. This really is a good example of using these tools. I just got stuck. Oh, we do have some weaknesses. We would really have preferred to remove the track bars, but we could not get it to tune automatically. And you could see between many of the pictures, the user variables required were just very different. So that's where we ended up. Searching for text. I guess that's pretty much it. I think everything else I hit on.
So that was Group 5's presentation. Thank you so much for listening. And do we have any questions?
Great job, Group 5. Excellent demo. Yeah, but I have to say, for a rule-based program, you certainly applied a whole lot of things you learned in the class. All kinds of filters and shape detection and all that stuff. So kudos to you on doing it. Let's open it up for questions.
Hi, I have one. Did you guys consider doing like a pattern matching and just having a database of license plates? Since license plates are, I don't want to say they're standard, but you could just do a standard pool of the Michigan plates.
We did consider that, but I was thinking about how many different license plates there are. I know you were saying it is like a set amount, but running like, let's say, a orb matching algorithm on it, each individual one of those plates, and storing all of those found features on the standard license plates, and then comparing those found features with every single video frame, because we didn't know a way to just set an ROI around a license plate found in a video frame. So we'd first have to do that and then run the matching algorithm with every single known plate. And that would have taken, I think, too much time to run that matching algorithm and still allow every single frame to be processed. So we wanted to go with something that would go fairly quickly, if that makes sense.
Makes perfect sense to me. Especially if you had a full database for every license plate, I'm sure it would have taken forever. So
That's a good question, though.
You guys talked about using machine learning, and that might have been also a good way to figure out what is a license plate on a car. And the nice thing about machine learning algorithms is it takes care of angular views or sizes. It kind of adjusts for that itself. Did you find any existing database of license plates to teach a machine learning algorithm? Were you able to successfully find any of those? I don't know if it exists or not. There's just a curiosity here.
I didn't specifically find one, but I know there must be a lot out there, because when I was doing research for this project and found the option to do machine learning near the end of our time frame to complete the project, I noticed that most algorithms that I found online used machine learning. Almost no one used a rule-based system like we did. So I'm guessing everyone just has the same idea, where that's probably a lot more robust than machine learning is a lot more robust than using a rule-based algorithm. So
Yeah,
I'm sure it exists out there.
And going into it, you're very hopeful that your results will work. So we were very hopeful. We thought our rectangular worked in various lab scenarios. And then when we ran everything, we were thinking, machine learning would have been a really great way to implement it had we had the time, and if we started testing it a little bit earlier.
I have to say that once you know how to use machine learning, it's pretty straightforward way to implement those and train it and then actually use it. What you guys did was you actually learned the hard way how difficult it is to make a rule-based system. But kudos to you that it did work. Even in live video, that's a difficult thing to achieve with all the rules you had. Just curiosity. When you were matching those rectangles for the license plate, and you had the rule of okay, is it really a rectangle? So you're taking the ratios of the side. What happens when you're looking from the side view? It's more of a trapezoid then. Did it work for that, or you had tolerances?
Yes, I actually, when I wrote that, I set it up so that it could be a little bit away from the ratio didn't have to exactly be 1. You can send in a parameter that estimates what percentage away you can be from the ratio equaling 1. And the way it's running right now, I think we're allowing for 30% tolerance, which is a pretty big amount.
Great.
So it can be as large as 1.3 or as low as 0.7.
So you think your algorithm will work on a Cybertruck, which is mostly rectangular?
We might just have to censor the full vehicle.
Are you down to sponsor us buying the vehicle and then we can test it out?
Well, okay. Well, we'll make it close to 99% success first.
Submit it for an Epic Mega Grant.
There you go. Okay. Any last questions for the group? All right. Great job again, Group 5.
All right, thank you.